Thank you, and thanks for the organizing for this very interesting week. And, well, I guess the whole program here, but I'm only here for this week. So I'm going to talk about some variations on Polya urns that various people have been discussing over the last 10, 15 years. I'll start with a bit of background, reminding you some things on the regular Polya urn. Yes, and I should mention, so James was complaining that the title is a bit ambiguous, in that it's not clear if the urns are interacting or Polya is interacting. So hopefully this will be clear by the end of the talk, but if not, then that's also good. So let's start just with a quick reminder. So I'm sure you've all seen the classical Polya urn. So you have this urn, which we'll draw like this. And you have balls inside it of various colors. So maybe we have red and yellow and some blue balls. And the classical Polya urn, you just say you pick one uniformly at random without looking. And which one did we end up picking? Which one did you pick? Yellow. Right, so we picked a yellow ball, so then we put in another yellow ball. And now we have 5 balls, and we pick one uniformly and random. And Perla, do you want to pick the next one? Yellow again. So we get another yellow ball. And Evita? Blue. OK, so we picked up a blue, and this was a bit less likely since there's more yellow, but we picked up a blue. OK, so you keep going like this. And we want to understand what happens. And this shows up in a large number of situations, a large number of processes that you model end up being related to this Polya urn. So let's just suppose that xt, let's say xt of I, so this is the number of color I at time t. And the question is, what happens to this asymptotically? And as I think many of you know, that for this classical Polya urn, the answer is that the x's are asymptotically proportional, so that each color has some asymptotic proportional density. So if you look at, so this is the most classical fact is that xt of I over t converges to some random limit. Let's call it wi, which adds up to 1. And there are many ways to see this. One thing that I'll maybe mention is due to Rubin, which is the observation that you can separate the color. You can just say that instead of picking in discrete time, each time pick a ball and this, you can just say that each ball is selected at rate 1 and splits into 2, gives. So what does this mean? It means that so each color I is increased at some rate x t of I. So if we have, so this is the Yule process. Each color you have a Yule process. It goes from n to n plus 1 at rate n. And you can analyze this using martingale. For this process, the consequence of, so now if you think of it in continuous time, and the fundamental observation, this is due to Rubin, is that up to a time change, you get the same sequence of balls, since the probability that you increase the ith color is proportional to the current population. So the classical thing that you can say about it is that xt of I asymptotically is some wi times e to the t. So this Yule process grows exponentially, and once we've done this, the processes are completely independent. So each process has this, where w is the limit of a certain martingale. It's almost surely positive. So wi is the limit of e to minus t xi, which is a martingale, so it has a limit. And the ratio between the different wi's give you the asymptotics. OK, so these wi's are not the same as those. Here, those wi's are normalized to add up to 1, whereas those wi's are just IAD variables for the different colors. But this, OK, so this is all very classic. You have the regular Polya urn, and all of the colors grow asymptotically. Each color will have some density of the some fraction of the colors. And then still fairly classical, you can consider some modified version where the probability that you pick a color is not proportional to xi, but proportional, yeah, so I didn't write the rules of the Polya urn, I just did this demonstration, but let's write about a modified version. So suppose that you enhance color I with probability which is not proportional to xi, but to x of I, but to x of I to some power alpha. And you can consider more general functions other than just powers, but to keep things a bit cleaner, let's stick to powers. So the probability is x of I to the power alpha, normalized, so you sum over all, let's call it j of x of j to the power alpha. So we have some parameter alpha governing the process. And so if alpha is 1, then we just have the classical urn. And if alpha is more than 1, then if you have a stronger color, then it has an even stronger advantage. If a color is twice as large as another, it's more than twice as likely to grow. So if alpha is more than 1, then you have a sort of rich-get-richer phenomenon. Well, all of these urns have a form of the rich-get-richer. The larger colors are always more likely to grow. But if alpha is more than 1, then this moves away from equality. If a color has twice as many balls, then the added balls are more than twice as much as the other color. If alpha is less than 1, then this is sort of a balancing effect. And indeed, you can use the same approach. So let's just make this into a red alpha so we can keep track of it. So if we just put here this alpha here, so now again, you get these independent processes where each color grows independently. But now the consequence of this is that, so in continuous time, so in this continuous time version where each color just gives rise to new balls of the same color independently of the others, what you end up getting is that xt of I is approximately, well, it depends now on whether alpha is less than 1 or more than 1. So you can approximate this by a differential equation. The derivative of the number of balls should be roughly like the alpha power. And if you believe this approximation with the differential equation, what you get is that it grows something like some constant t to the 1 over 1 minus alpha. Well, this is if alpha is less than 1. You have some problem? Or no? Yeah, so if alpha is less than 1, it grows like some power of t. If alpha is more than 1, then it actually blows up in finite time. So, and tends to infinity at some time, let's call it tau, which is finite if alpha is more than 1. So that's what happens if you separate these colors. Each color grows independently. So what does this tell us about the discrete time process? So in the discrete time process, if alpha is less than 1, so this constant is just a fixed constant. I don't remember what it is, but you can calculate. So if alpha is less than 1, then all of the colors grow sublinearly, and asymptotically they will all be equal. The ratio between any two colors will converge to 1. So a consequence of this is that if alpha is less than 1, then xt of I over t converges to 1 over the number of colors. Whereas if alpha is more than 1, then at some finite time in the continuous time process, at some finite time, one of the colors tends to infinity. And all of the other colors are still finite. This explosion time tau is a continuous variable. So that means that at some time, one color will go to infinity and all the others are still finite. So this means that one color wins. So xt of I goes to infinity and the others are bounded. So the other colors do not grow beyond a certain time. And so this is all fairly classical things that is sort of the background for the for the models that I'd like to talk about. But if there's any questions about anything I said so far, then please do interrupt. So OK, so where do the interactions come in? So the interactions were introduced by two separate groups. So one is in a paper of Benaim, Benjamini, Chen, and Lima, and another is in a work of van der Hofstad, Holmes, Kuczynski, and Ruschel, both from about 10 years ago. That's not he, that's Kuznetsov. Sorry, apologies. The T is not here. There's only one T here. Kuznetsov. Yes, so indeed, yeah, a lot of these conferences are like this, right? You have a bunch of mathematicians and you take one out and put one in and you end up with various groups. So yeah, so you can see where these models come from. So so they introduce somewhat different versions of this process, but what is the general idea is that at each time you have some Polya urn, and we will look at this modified version with some power alpha, but at each time not every color participates. So let's maybe move here, and so at time t, we are going to pick some set ut of colors. So it could be all the colors, but it could be, well, if it's all the colors, then it's just what we did before. If it's just one color, it's not interesting, but we pick some subset of the colors, and we just run the competition just between those colors. So you enhance one of ut. So you enhance, so xi goes to, so x of I goes to x of I plus 1 with probability x of r to the power alpha over sum over all j in ut of x of j to the power alpha. So you are no longer competing with all the colors, but each time just a subset of the colors are competing. And we want to try to understand the same type of questions. So what happens asymptotically in this model? Which colors? So if alpha is more than 1, do we get a similar phenomenon where some colors win and other colors remain bounded? And how many colors win? If all of the colors survive, then what are the asymptotic growth rate of the number of balls of each color? So do we have something like the proportional, like the linear growth where each color has some fraction of the balls? Or do we have some more complicated behavior? And it turns out that you get a much richer structure, even for the simplest case. So maybe the simplest case, which is the first case that Itai Benyamini was asking about. Suppose you pick just 2 colors each time out of n colors. So you have n colors, and at each step you pick uniformly 2 of the colors. Let's say today we have red and green. So today we enhance either red and green, and then tomorrow we pick again 2 colors, maybe red and yellow, and then only red and yellow are in competition, and one of them is enhanced. And in this case, even if alpha is more than 1, you have this very strong reinforcement where a strong color tends to run away and leave the rest behind. So you can't actually get that because there will be some times when the strong color is not in the competition. So okay, so it turns out that, again, even for the case of the complete graph with k colors, it's a bit tricky to analyze all the possible asymptotic behaviors.
You haven't told us how you pick the color sets yet.
I haven't, yes. How would you like to pick the color sets? So as I said, the classical version, one example, the first example that Itai was asking about, so UT is 2 uniform colors. So we just pick 2 of the colors at uniform.
Distinct colors?
Let's say distinct. You can also allow for, with some probability, to pick just 1 color, and then you just have this 1 color going. If you do that, then of course all the colors grow linearly just because of the times that you pick just the 1 color. But if you always pick 2 colors, then it's not clear. It's possible that maybe 1 color stays behind. But the most general framework is that you have some distribution on these sets U, and each time you pick from this distribution. And you can ask this, so there's a very large family of models that you can analyze here. So there was the original paper of this Benaim and others, which was on this version where you pick 2 colors, but not 2 uniformly colors. So this Fay paper, let's call it 1. So in 1 you pick, so UT is an edge of some graph G. So you have a graph on the set of colors, and each time you pick an edge, and only the 2 colors so the colors sit on the vertices, and you pick one of those. And there was a follow-up work by Chen and Lucas where they got some additional results. So on this case, the works of Remco and the others, so they considered sort of a reverse, the other extreme case. They also had a graph G, but for them the colors were on the edges. So this, so let's call this 2. So in 2, they defined what they called the worm model. So what is this worm model? Okay, so let's maybe move the board. Okay, I can skip. I can move it later. So so the colors are the edges of a graph. And UT, so these are the edges at some vertex V. So each vertex you pick so you have some probability of picking each vertex, and then you reinforce one of the edges at that vertex. So you can think of it for a model for some group of friends. So you have some group of friends, and occasionally one of them hears some juicy bit of gossip, say about the sexual preferences of a former president. Are we allowed to say this here? I'll assume yes. So someone hears this rumor, and okay, so they quickly call one of their friends, and they tell them the rumor. So you have several friends, and you have some graph of acquaintances between them. And then one of them hears the rumor, and they pick one of the friends proportional to the strength of the friendship, and call and tell them the rumor, and this causes the friendship to be reinforced. So the edge is now a bit stronger. And then later, maybe this guy hears a rumor and decides to call here. So this edge gets reinforced, and then maybe this one hears a rumor, and she says, well, this one I've already talked to recently, so they're more likely, so they reinforce it even more.
There's no chance that the rumor will be so revolting that the relationship will deteriorate?
So, no, that's a good question, and indeed there are many variations on this model. So for the time being, I was saying each time when you reinforce one of the colors, you increase xi by 1. But yeah, so you can certainly consider variations, and some of the methods work where you increase xi not by 1, but by some other amount, and you can also allow a random amount which might be negative. So if it tends to be negative, then things will behave very differently, and I'm not sure what I can say about this without thinking. But if you have a bit of negative reinforcement, then a lot of things will still go through, but certainly some of the proofs will break. So but yeah, there are numerous possible generalizations beyond the things I'm going to discuss today. Yeah, but so here, as we said, so for every edge we have so xt of e. So this is the strength of the edge e at time t. And so these are undirected edges in this model. If you wish, you can also consider directed versions. But the directed version is less interesting, because in the directed version, if you just consider all of the edges going out from a vertex, then this is a separate set from the edges from all of the other edges. So then you just get independent Polya urns, one for the outgoing edges from each color. Whereas if it's undirected, then you do get the interaction. So you can think of it that you have at each vertex, you have a Polya urn between the colors of between the different edges exiting this. But these urns are interacting. For example, if this vertex chooses to enhance this edge, then this vertex is then more likely to enhance the same edge as well. So this edge participates both in the urn at this vertex and in the urn at that vertex. So this is what they call the worm model, for reasons that may or may not be related to the acronyms of their first names. Okay, and so that's the model, and there are lots of different questions that you can ask. I'm going to to discuss some results about different regimes. And much like in the case of the classical Polya urn, the big distinction is whether alpha is less than 1 or equal to 1 or more than 1. That should not be too surprising. But a lot less is known, and there are lots of conjectures and things that we don't yet know how to prove. So let's start with the case of alpha equal 1. That's the most classical case, but not that much is known in general about this. I should mention, by the way, that you can also do, when the graph is finite, you can pick a vertex uniformly at random or with respect to some distribution on the vertices. But you can also do this for infinite graphs, where for every vertex, you have some rate at which you pick this vertex. So you can do this, for example, on ZD, where every vertex you pick with some at rate 1, and you reinforce one of the edges connecting to it. So in the linear case, where alpha is equal to 1, so okay, so for the graph model of this Benaim and others, where the colors live on the vertices of the graph, it is known, at least for finite graphs, that it always converges. This is a work of Chen and Lucas, that the ratios of the xi's converge. But in general, this is open. There are also some works of Holmes and Kleptin, works in progress, where they also do this on some graphs. But let me maybe mention one of the open problems here that I like. So suppose the graph is just the infinite line. So you have the infinite line, and suppose that initially at time 0, x0 of I is all 1. So initially, every edge has strength 1. And again, every vertex at rate 1 you pick, and you reinforce one of the two one of the two edges, proportional to the current strength. Okay, so prove that x t of every edge I is approximately t, in the sense that the ratio tends to 1. So if you do things on a cycle, then we do know what happens. And it turns out it depends actually on the length of the cycle, depends on whether it's even or odd. So let's use Zm for the cycle. So if m is odd, then you get the same behavior. If m is odd, then all of the edges are asymptotically equal. So if m is odd, then x t of every edge E, let's switch from I to E for the edge, is asymptotically t. So all the edges are asymptotically equal. If m is even, then x t of E converges to some limit as t goes, or let's say divide by t. This converges as t goes to infinity to some u if E is an even, and to 2 minus u if E is odd. So you get alternating behavior where the even edges have one strength and the odd edges have some other strength, where u is a random variable. It's not clear what is the distribution of u, but if you take a cycle of length 2, the cycle of length 2 is just 2 edges, and this is just a classical Polya urn. And you can sort of see why this sort of thing might happen, because if you have an odd cycle, if you have an edge that is very strong, so what is the effect of this? This means that the edges nearby it are somehow at a disadvantage. Since they compete with the strong one, they are less likely to get reinforced. So if you have a strong edge, the ones nearby it are slightly weaker, then the ones away from that are going to be stronger because of that. And the ones after that are going to be weaker, and so on. And then the question, what happens when you go around the cycle through this chain of correlations? And if you have an even cycle, then if you have a strong edge, you find that after going around the cycle, the edge still reinforces itself. If you have an odd edge, then it actually works against itself. So if you have an odd edge, after the influence goes around the cycle, the strong edge tends to reduce itself. So this is sort of an intuition for why this is what you might expect. And indeed, this can be proved. Yeah, the fact that you get these different behaviors sort of highlights some of the difficulty of what happens on the infinite line. Since one of the natural approaches for any one of these models, I should discuss there's a very natural approach to study it, which is the dynamical approach. You can say if you have some fraction of so let's suppose that S of E, so this is xt of E divided by t. So it's just the fraction of edges. And you can try to treat this as a dynamical system on this vector of S, on the vector S. So you given the vector S, you know the relative size of each of the edges. And you want to ask, is this going to be, so you have some distribution on the size of the strength of the colors, and you want to know how does this evolve over time. And when you make a large number of steps, then you can expect, okay, so if you make a large number of steps less than t, little of t, but still large, then the densities, the relative strength do not change much over this time period, so you have approximately independent increments. So you can expect that the S will grow according to, will evolve according to their expected growth. And then you can say, well, what is the equilibria? What is the set of equilibriums? And you find that you have an equilibrium. An equilibrium is some set of of strength mu, such that mu of E is just equal to mu of E to the power alpha. It should be equal to the rate at which it is reinforced. So you want every color or every edge to be reinforced at a rate which is given by its current strength, and then the strength don't change overall. So it will be this divided by mu of E, let's use E plus and E minus. So you have, so this is the, sorry, that's not the right formula. Sorry, so you want mu of E to be the probability that an edge is reinforced. So this should be mu of E to the power alpha divided by the sum over all edges E prime containing, let's call it, let's say that the edge E is some xy. So you want all the edges containing x of mu of E prime to the power alpha, plus the same thing with the sum over y of mu of E prime to the power alpha. Right, so this is the probability that the rate at which an edge is reinforced from x, and this is the rate at which it's reinforced from y. So you want the overall rate at which an edge is reinforced, and I'm assuming here that every vertex is activated at rate 1. If you have different activation rates for the vertices, then you get some things showing up in this formula as well. So you get this equilibrium, and and if S happens to be an equilibrium, then you expect that it shouldn't change much. If S is not at equilibrium, then you can also say, well, it's going to flow according to some version of a gradient descent related to this. So it's going to flow more or less deterministically, and it should flow towards an equilibrium. The problem is that even for finite graphs, finding the set of solutions to this seems tricky, and it's not clear. It's not obvious a priori that there has to be an equilibrium even. Just you write this set of algebraic equations. Well, algebraic if alpha is rational, but you have this set of equations. It's not completely obvious that there has to be a solution even. Of course, if alpha is larger than 1, you could have some degenerate solutions where some of the mu's are 0, corresponding to edges that get stuck and other edges that grow. But this is a general equilibrium condition, and a lot of the works that were on this model involve trying to understand these dynamics in one way or another. So if you go back to this case of the linear case, alpha equals 1, so for alpha equal 1, the problem is that there's no unique equilibrium. So on the even cycle, so for any u, this will be an equilibrium. So the set of possible equilibria, and on the infinite line as well, any set of alternating weights, u and 2 minus u, will be in equilibrium. So so this complicates and rules out various ways of trying to prove that you must converge to the equilibrium. And in particular, you could have various things that are almost stable. If you have a large interval in the line that roughly alternates between u and 2 minus u, then it's going to take a very long time for the influence from other regions of Z to percolate. So the rate of convergence here is probably going to be quite slow, and I don't have a good guess for what it is. But this is maybe one open problem for the case of alpha equals 1. There are lots of other questions one could ask. But let me switch and talk a bit about other cases, alpha more than 1, alpha less than 1. So alpha more than 1 is this, for the classical Polya urn, we said one color is going to win and they go to infinity, the other colors remain finite. And if you do this for this worm model on a graph, then certainly at every vertex you must have at least one edge that goes to infinity, because the vertex is activated infinitely often. So certainly at least one edge at every vertex must diverge. Let's move back here. So So this is the supercritical case.
Say what you're saying again. Why does every vertex get activated? Maybe at the
Yeah, so we say that, okay, so this is all in discrete time now. Well, okay, so let me say, so if you have a finite graph, you can say that every vertex is picked, you pick a uniform vertex and reinforce an edge at that vertex. If you have an infinite graph, then every vertex is activated at some rate, let's say rate 1, and then you reinforce one of those. So, right, so that's the model that we take. We pick a vertex, every vertex at some rate, which could be always 1 or could depend on the vertex, and you reinforce one of the edges at that vertex. So if alpha is more than 1, so let H be all edges such that xt of E tends to infinity. So this is a subgraph of the original graph that we started with. So what can you say about this subgraph? And there are some results about what this subgraph can and cannot be, but generally not too much is known. So the question is to understand H. So it has no isolated vertex. So it's a subgraph and it cannot have isolated vertices because as we're saying, every vertex is activated infinitely often. So infinitely many times you reinforce one of the edges at that vertex. So at least one of the edges must go to infinity. So there's a subgraph with no isolated vertices. So it can have some cycles. It doesn't have to be a tree. So there is a theorem. This is Hirsch, Holmes, Klepsin. So on ZD, if alpha is large enough, which is generally something large, so H has no percolation. So there's only finite components in H. And conjecture, so that is that this also holds for any alpha larger than 1. However, the proof of this, yes, Rick.
What happens on a small finite graph, like a triangle?
So yes, so indeed, also on the finite graphs, there are some. It's an interesting question, and there are non-trivial things. So you could get all 3 edges on a triangle, depending on alpha, or you could get that 2 of the edges diverge and 1 stays. But it is possible for some alphas.
Different behavior depending on alpha.
Yes. You do get different behavior depending on alpha. The conjecture is that.
It's not proved. I mean,
well,
is that a proof? I mean, is there?
So for the triangle, certainly it's true. So I think there's at least I believe, and I'm not sure if this is proved already or not, that if alpha is close enough to 1, then for any finite graph, it's possible that all of the edges diverge if alpha is close enough to 1. So at least you do have some stable things, some stable asymptotics that give that. But for ZD, the proof of this, you can show that there's no infinite percolation, but the proof is a perturbative proof, and it's a perturbation around alpha equals infinity. So what happens at alpha equals infinity? You just say you reinforce the strongest edge next to you. If you have ties, then you toss a coin, but you always reinforce the strongest edge. So that means you always prefer to reinforce an edge that already has been reinforced over an edge that hasn't been reinforced. So that means every vertex, if you activate a vertex and none of the edges next to it have been reinforced already, then you pick a new edge. But that's the only time at which you are going to pick a new edge. So basically every vertex, you can say, every vertex has some edge going out of it, which is the edge that we reinforce from this vertex, and no other edges will be reinforced. So this model is not too hard to show that there's no, so if you take ZD and for every vertex you pick one outgoing edge, and you look at the set of all edges that you pick, this will have no infinite clusters. This is not too hard. And when alpha is sufficiently large, you can show that the model is very close to this. So for most vertices, you will basically just have one outgoing edge that you activate. You do have some small density of vertices that misbehave, but you can still show that there's no infinite clusters. But as you said, this is a perturbative proof, so I'm not sure how big alpha needs to be in terms of D, but certainly it's something that can be worked out from their proof. But it's not going to be close to 1. So this is another open problem, what happens on ZD for alpha more than 1. On trees, it is possible to get infinite clusters for some alphas. And again, I don't think we know the precise critical alpha for getting an infinite cluster on a regular tree. But that's also a question some of you might want to think about. Any questions about alpha equal to 1, alpha greater than 1? Otherwise, I'll switch to alpha less than 1.
There's no results for alpha equals 1, right?
There are some results. There are some in a paper of Chen and Lucas, some earlier, and there is some work in progress of Holmes and Kleptin. But okay, so for the final few minutes, I want to talk about alpha less than 1. And the expectation when alpha is less than 1 is that things stabilize. So the expectation is that there should be some equilibrium, ideally a unique equilibrium determined by the graph, and you should converge to this. So the general conjecture is that xt of E over T converges to some mu of E, which is a unique equilibrium. So it's a unique equilibrium satisfying this, which you can derive out of the graph. If you have completely arbitrary graphs with unbounded degrees, you can get some kind of ridiculous things happening. So let's talk about graphs with bounded degrees. So Cousini and Hirsch have a paper from a couple of years ago. So let's call this star. And this is, let's call it double star, that mu is a unique equilibrium. So they were able to prove that this holds in some cases. Well, they proved it if you have bounded degrees and alpha less than half. For a bounded degree with alpha less than half. And also if you take the line z for alpha less than 1. And they proved it a bit beyond half for regular graphs also. They don't show that the equilibrium is necessarily unique. They show that you converge to some equilibrium. Though for alpha small enough, you can also get that the equilibrium is unique from that. And this is basically a dynamical approach. So the idea is that if you have some equilibrium, you say, suppose you are not too far from the equilibrium. And if you're not too far from the equilibrium, then you can say, well, what does the growth rates of each edge look like? And you find that you're going to be a bit closer to the equilibrium. The growth rates are a bit closer, so asymptotically, you are pulled back. So it's some kind of a bootstrapping argument where if you are inside, if the equilibrium is here, if you are in some interval here, then later on you'll be in some smaller interval and smaller, and eventually you converge. And this works there's all sorts of inequalities that are needed there, which break once alpha is more than a half. So so maybe to finish, I want to show you a very different method that we have for showing this, which works which works all the way up to alpha equals 1. And also works for certain infinite graphs. For any finite G, and or for if G together with x0 is unimodular. This is more general. So if you look at the graph together, unimodular and regular, and well, we may be able to get rid of the regularity assumption here, but at the moment we still have this. If you're not familiar with unimodularity, given the time, I probably will not say what it is, but you can ask me later. But certainly for any Cayley graph, and also we can say for G transitive with x0 constant. So if you have constant things, then any transitive graph is fine. So, and again, one of the open problems that we are still unable to do is to show that this works for arbitrary initial conditions. So it seems that if you take a completely arbitrary initial conditions thing, as long as the graph is reasonable, it should still converge. And for finite graphs, this is fine, but for infinite graphs, we are still missing some pieces. And let me just show you the idea of this, and I'll show you.
For the theorem, it holds for arbitrary initial conditions for those two classes.
So here we need the initial conditions also to be part of the unimodular sum. We need that together with the decoration of the initial things is unimodular.
And what is it in the transitive case then? What is in the transitive case? What is your?
What is what?
What initial conditions? I mean that.
With constant initial conditions. Initially, all the edges have the same strength.
Okay.
Yeah. Yeah. So you need all the edges are initially equal.
Oh, you confuse me because I thought for a moment x naught was the root. That's why I confused me.
No, x naught. Sorry, x naught is. So yeah, so x naught is the initial strength. So because you can consider this not just when initially you have all strength 1, but other strength as well. And
This is for all alpha less than 1?
yes, for every alpha less than 1. Yes, thank you. And I'm out of time more or less, so I'll just say show the idea of in the simplest case of a finite regular graph, and the idea is as following. So let's define some function f of n, which is just the sum of I less than n of I to the power minus alpha, which is roughly n to the 1 minus alpha, well, with some constant. And let's consider the following quantity. I'm going to consider the sum over all edges of f of xt of e. So at time d, I'm just going to consider this sum. And I'm going to ask, okay, so since I'm running out of time, I will not write the different steps, but so what's the idea? So on the one hand, I claim that this function alpha is less than 1, so this function f is concave. So that means that H is maximized when all of the edges have approximately the same. So given the sum of the edge weights, this is maximized if they're all approximately equal. And for a regular graph, the equilibrium is when they're all equal. So now the sum of the edge weights, the sum of the edges is just the total number of activations we've had so far, which is just a Poisson random variable. It's certainly very concentrated. And given that, we know that H is maximized if they're all equal. On the other hand, we can ask what is the rate at which H grows? The rate at which H grows, so if we increase f of x, if we increase some x of e, then it grows by x of e to the minus alpha. And you do some calculations, and you need to use some inequalities. You need to use Jensen and Helder in various ways there. And you end up showing that the rate of growth is minimized also when the edge weights are all equal. So if the edge, and if you run through the calculation, it tells you that the expected value of H at time t is fairly close to its maximal possible value. And all of these inequalities, you have some, you can quantify, and you can say, well, if you are far from all being approximately equal, then you actually lose something in the inequalities. Yes, yeah, this is strongly concave. Alpha is strictly less than 1. And the conclusion of this, so H must be, with high probability close to its maximum, given the sum of the x of e. And this implies that the x of e's are all approximately equal. So this is for the regular graph, and this is quantitative. You even get some rate of convergence for here. You get something like t to the alpha minus 1 rate of convergence here, which we don't believe to be the true rate of convergence. That's another question to improve the rate of convergence. So this is for the regular graph. For the general graph, you need to stick in the equilibrium here if the graph is not regular. And if in the unimodular cases, you need to replace this sum by expectations at a random vertex. There are similar methods, but some additional technicalities. Okay, but I'm already over time, so let me stop here.